Good morning. Our today's topic is frequency modulation. In the last class, we have discussed amplitude modulation. So, in frequency modulation, frequency of the carrier signal is varied in accordance with the instantaneous amplitude of the modulating signal. What about amplitude modulation? In amplitude modulation, the amplitude of the carrier signal is varied in accordance with the instantaneous amplitude of the modulating signal. In frequency modulation, the frequency of the carrier is varied. So, in frequency modulation, the amplitude of the FM signal remains constant, or the amplitude of carrier remains constant. The modulation index MI is equal to the frequency deviation of carrier divided by the frequency of modulating signal. This is the general equation for unmodulated carrier, or this is the equation for carrier before modulation. So that is Vc is equal to Vc sin omega Ct plus phi, where Vc is equal to the instantaneous value of voltage or current, and this Vc is equal to the maximum amplitude. Omega c represents the angular velocity and phi is the phase angle. Let's see the definition of deviation. Deviation is the amount by which the carrier frequency is varied from its unmodulated value, and the rate of deviation depends on the modulating frequency f. So please note these 2 points: deviation and rate of deviation. This is the waveform representation of modulating signal, carrier signal, and this is the FM signal. So this is the modulating signal. We already discussed this modulating signal. Then this is the carrier signal, that is Vc, modulating signal Vm. Here the amplitude of the modulating signal is represented using letter A and minus A. That is it represents the amplitude of carrier. So this is the FM signal. So in FM, only the frequency of the carrier wave is varied. Amplitude remains the same. So the same amplitude A and minus A represented here, A and minus A. The amplitude of carrier remains constant. Only the frequency is varying. Consider this positive half cycle of modulating signal. So during the positive half cycle of the modulating signal, the carrier frequency is increasing. Frequency increasing. So consider this period. So you can see here the time period decreases. See the time period is decreased. Time period is decreased means frequency is equal to 1 by time period. So the time period decreased means frequency increased. So in this time period, or in this portion corresponding to the positive half cycle of the modulating signal. So in this positive half cycle of the modulating signal, the frequency increased. That means the time period decreased. Let's see negative half cycle of the modulating signal. During this part, that means during the negative half cycle of the modulating signal, the frequency decreased. So you can see the time period is increased in this portion. That means frequency decreased. Again, there is a positive half cycle. Time period decreased. That means frequency increased. Again, negative half cycle. Time period increased. That means frequency decreased. So this frequency increased, frequency decreased, frequency increased, frequency decreased, shown this FM signal. So this is the frequency variation. Okay. So the amplitude of the carrier signal remains constant, only the frequency is varying with respect to the instantaneous amplitude of the modulating signal. So this signal represents FM signal. Let's see the mathematical representation of this frequency modulation. The instantaneous frequency of FM is represented like this. F is equal to Fc into 1 plus kVm cos omega mt. That is equation number 1. Where Fc is the unmodulated carrier frequency. Fc means carrier frequency. K is a constant, or it is the proportionality constant. And Vm cos omega m. This is Vm cos omega m. That is the instantaneous modulating voltage. Instantaneous modulating voltage. So let's see the frequency modulated vector. This is the frequency modulated vector. So in this vector you can see theta is the angle, and it is used to show the deviation, the frequency deviation. We know that omega is equal to 2 pi fc. So the frequency deviation from t is equal to 0 to t is equal to t is shown here. Theta is the angle. So we know the equation number 1, F is equal to Fc 1 plus kVm cos omega t. The maximum deviation possible when this cosine term gets its maximum value plus or minus 1. When cosine term gets its maximum value plus or minus 1 means there is maximum deviation. So substitute cos omega mt is equal to plus or minus 1. So we will get F is equal to Fc into 1 plus 1 plus or minus kVm. Cos omega mt is equal to plus or minus 1. While expanding this equation, we will get Fc kVm. So this Fc kVm is equal to delta, that represents the maximum deviation, that is equation number 3. Let the instantaneous amplitude of FM signal V is equal to Vc sin f of omega c comma omega m, which is equal to Vc into sin theta, where theta is equal to a sum function. It is equal to f of omega c comma omega m. So instead of f of omega c omega m, substitute theta. We know that omega is equal to 2 pi f. So equation number 1 becomes, so equation number 1 means equation of frequency, first equation. So omega is equal to 2 pi f. So we are applying omega is equal to 2 pi f in that equation. Thereby we can write equation number 1 as omega is equal to omega c into 1 plus kVm into cos omega mt. So in order to find out the theta, so theta is a sum function, or it is the angle. So it is equal to integral omega dt. So integral omega c into 1 plus kVm cos omega mt dt. So we will get theta is equal to omega c omega ct plus delta by fm sin omega mt. That is equation number 5. So this fifth equation put fifth equation in fourth equation. So here we calculated theta, apply the value of theta in this equation. So we will get V is equal to Vc sine omega Ct plus delta by Fm sine omega Mt. Okay, and the modulation index is Mf, that is delta by Fm. That is equation number 7. If you apply equation number 7 in equation number 6, we will get the instantaneous amplitude of Fm as V is equal to Vc sine omega Ct plus Mf sine omega Mt, where Mf is the modulation index. Thank you.